Hi everyone, I'm Kamashanta Krishnan.
Hi, I'm Praveen Ravisankar, and our project was to best classify optic nerve sheath dilation in order to determine elevated intracranial pressure.
Just as some further background, I'm a third year undergraduate student here at UCI. I'm a biomedical engineering major, and my research interests are primarily diagnostic technology development and bioinformatics.
I'm Praveen, and I'm a third-year undergraduate data science major here at UCI, and my research interests primarily involve biostatistics and natural language processing.
Just as some background on our project, the primary problem we're tackling is that medical professionals lack an automated means of measuring and analyzing the diameter of optic nerve sheath diameter of a medical patient. Current means are rather subjective and prone to errors due to how a medical professional has to interpret an ultrasound image themselves. This can lead to problems with accuracy, time consumption, and also requiring proper training and equipment. Here is an example of the use case of ocular ultrasound as shown with a probe on a patient's eye and a subsequent image.
So why are ocular ultrasounds interesting? Right now, most of the diagnoses that happen for elevated intracranial pressure have to go through a whole medical procedure where you go to the hospital, get a CT scan, and then they're able to make a diagnosis through analysis of the scan. Or the doctor gives a quick subjective diagnosis based on symptoms and questions that they ask. However, hopefully with our algorithm, we believe that using ocular ultrasounds in a portable fashion will help us determine elevated intracranial pressure immediately and objectively. And research about the subject is currently being done at UCI. So that's why we thought of pursuing this.
Our data sets primarily that we worked with have been these three listed here. The one we honed in on ultimately were cranial ultrasounds from the National Biomedical Imaging Archive, primarily due to their clarity, their standardized format, a DICOM format that's normal with most ultrasounds, and the clarity of the optic nerve discs we were looking for.
So our solution was to use segmentation and image segmentation and augmentation in MATLAB, and then classifying it with a CNN to best measure the optic nerve sheath diameter.
We would start by augmenting and segmenting the image. The DICOM files would start off as being red. We would define different regions on a graded scale based on pixel to pixel variation. Similar pixels would be grouped together within a established range. These groupings would be made more distinctive via binarization and denoising as some processing. And we would separate these segmented regions into separate frames and move forward with a frame that has the optic nerve disc.
From there, we would take these pre-processed images and actually use them to set and run our convoluted neural network model. We would first have to standardize these images to make sure that they were all the same frame size. And then from then, we used a sequential model with a linear stack. And we were actually able to increase the number of convoluted 2D layers in order to build a deeper model and flesh out the attributes that we wanted. We actually were able to augment our model with a pre-trained Keras VGG16 that's used for image classification in order to best improve our accuracy. In order to fine tune our model, we ran through a bunch of for loops to best determine the number of epochs and the step size we needed to take to get the highest accuracy. And from that, we were able to get an epoch size of 30 and a step size of 500.
Through model validation, we used a 70-30 training validation split with our data. We ran across the validation set in order to make sure it's acceptable, matching it against MSEs. We had the validation sets used with predetermined ICP levels to test them with as a benchmark and made sure that there was no training errors or biases in the process.
Yeah, so a big problem with our project when we started out was the fact that we didn't have enough data to actually um, do it as well as we wanted to. And in order to skirt around this problem, we actually got an expert evaluation. We reached out to the medical professionals and research professionals that were pursuing the subject matter at UCI, and they actually helped us validate our model and look through the predictions that we made and made sure that they matched up.
In conclusion, we believe that our model can help effectively classify a patient's ICP based on their ocular ultrasound in a way that's either normal or elevated.
And we believe that the applications for this are endless. Like if we are able to integrate our algorithm with a portable ultrasound device, we'd be able to make speedy and objective diagnoses of elevated intracranial pressure on on like a football field or in an ambulance, which could lead them to figure out if they have experienced head trauma, concussions, or even tumors. So thank you so much for listening to our project, and please let us know if you have any questions.